Some functions are defined as integrals, i.e. some functions are defined as the area under a curve. Okay? The most famous, notorious, whatever you want to call it, would be the natural log of x. That is actually defined as the area from 1 to x under the curve 1 over t dt. Why is it x? I'll show you. Oh, what?
No, like the entire function is like that.
What's the
E.g. ln, natural log. Have you not seen the natural log? I know, but you'll see. Okay.
Don't say that. He's gonna like.
So here's the graph of 1 over t. Okay? Or 1 over x. The natural log function says is defined as this. The natural log is the area under this curve from 1 to whatever you make x. So if I say, what is the natural log of 2? Right? You put that in your calculator. That is equal to the area under the curve from 1 to 2. So this x would be a 2. So punch it. What's the natural log of 2? Natural log of 2 is 0.693. Okay? What? For the natural log function, yes. This is a special case. Okay? So the natural log of 2 is 0.69, so this equals 0.693 or something. That means this area, or I'll just draw it right below. That means the area from 1 to 2 of that function is 0.693. That's what you're doing when you do the natural log. You're actually finding the area under the curve 1 over t from 1 to whatever number you punch into the natural log. Of the natural log?
Yeah.
Okay. So the natural log function is defined as the area under the curve 1 over t. This is the curve 1 over t. This area, this red bit, which will vary. The thing about the second fundamental theorem says that this top number is a variable. It moves because it's a function defined over an integral. Okay? So it's like a slider. It's going to move back and forth. So if I'm doing the natural log of 2, I put 2 in wherever there's an x. So I get the integral from 1 to 2 of this curve. If you punch natural log of 2 in your calculator, you'll get 0.693. That means the area from 1, and so we've said this is 2, is equal to 0.693. That's all it means. Okay?
So 0.693
is this area if I make that a 2. If I make that a 3, whatever the number is the area from 1 to 3 under the curve. Okay? So basically it's functions that are defined as integrals. Okay? So what happens when you do the derivative of one of these functions? Okay? So if we have the second fundamental theorem, I understand it can kind of confuse people. So we go f of x is equal to that's our function. Okay? It's defined as the area under the cosine graph. Okay? So if you remember, you don't have to draw the graph ever, unless they ask you to, but I'll just draw it for a visual representation. Okay? So the area, call this x, and then x slides, right? Depending on what you want to make x. That make sense? That's all this function is saying. It's saying this function has a value that is equal to the area under the cosine curve, from 0 to some whatever arbitrary number you pick for x. Okay? What if I say I want to do the derivative of this? I want to know what capital F primed is. That's what I want to find out. So I'm going to show you two ways to do it. Okay? The long way and then the shorter way that everybody will use. The long way is, if we're going to evaluate this function, I go, okay, let's do the antiderivative. What's the antiderivative of cosine? Negative sine, right? Or is it sine or negative sine? Sine, because the derivative of sine is cosine. Yeah, so it's positive sine. So it's sine of t evaluated from 0 to x. That's me just looking at, I'm just evaluating this, okay? And then I plug in my values. So I get sine of x minus sine of 0. Is everybody with me? Okay. This is f of x, right? It's the same thing. I've just evaluated the integral, and it gives me this. Now, I want to know what f prime is. So f prime, well, I take the derivative. What's the derivative of sine function? Cosine function. What's the derivative of this? It's 0. Why is it 0? Because it's a constant. Okay? This is a constant. Constant, therefore, derivative equals 0. So that goes away. So we end up with this. What's the fast way without going through all this stuff to get to here? How can I skip all the red stuff to go from this one, top one, just straight to the bottom? What essentially did I do?
Well, you don't
Change the variable.
You changed the variable, right? You essentially just took this x and plugged it in there. Because a derivative and an antiderivative, or an integral, are like the opposites of each other, right? So when you evaluate the integral, you get this. When you do the derivative of this, you basically just cancel everything you just did, right? And you get back to this. The only thing that changed was this. Does that make sense?
Yeah.
Because they're opposing processes. So they essentially cancel each other out. That's not quite what's happening, but that's sort of the idea, okay? Now, what if we do this? If I say f of x is equal to okay. So same function, cosine of t, except we changed the upper bound. Okay? We'll do it the long way, and then we'll do it the short way, and hopefully you'll see the quick. Okay? 7. But it doesn't really matter. It could be anything, as long as it's a constant. Okay? So what's the antiderivative of cosine? It's sine. We're evaluating it from 7 to 3x squared minus x. Okay. That's f of x. I just expanded the integral. Now I want f primed. So I go backwards. So what's the derivative of sine of 3x squared minus x? What rule do you need to use here? The chain rule. Chain rule says derivative of sine, which is positive. It's just cos. Cos of 3x squared minus x times what? Yeah, the derivative of the inside. What's the derivative of 3x squared minus x? 6x minus 1. What's the derivative of sine 7? 0, because it's a constant. So you're done. That's it. How do you go from the top to that without doing anything in the middle? There's only one extra step.
Then the derivative of the top.
Yeah, you have to use chain rule, right? You basically just plug this into your variable, so you get cos 3x squared minus x, but you have to remember to multiply by the derivative of that, which is 6x minus 1. That's it. Okay? Are we all right with that? Okay. Now I'm going to do a little amendment video for my Math 100 people because I made a mistake in it this morning. So I'm going to have to, this isn't for you, this is for them. Okay? But you can watch and copy it down if you want. All right, Math 100 people, this is for you. All right, so this morning we did this integral. Or sorry, this function. And I said you could just plug it in and get cos squared of x times, what's the derivative of cosine? Negative sine, right? I said that. That is not right. Okay? What you have to do, my mistake is, that's not right. What you have to do is you can put in the cosine and get cos of x all squared plus 1, and then multiply that whole thing by the derivative of cosine. And the derivative of cosine is negative sine. Okay? And then that's the answer. And the way you can show that is because if I do the long method and I expand out the t squared plus 1, I'll get t cubed over 3 plus t evaluated from negative 4 to cos x. And then I plug in the cosine. Cos of x cubed over 3 plus cos of x minus, and then it's going to be negative 4 in there, but it's all going to be constants, so I guess I'll write it out. Minus 4. Then you do the derivative, drop the 3. I'm going to get cos squared x. Got to remember to multiply by the inside derivative, which is negative sine of x. And then I take the derivative of cosine, which is negative sine of x. That all goes to 0, and I get that. That is the same as the one above, because if I factor out a negative sign, I get cos squared of x plus 1, which is that one. Okay, so just remember, if there's an addition or subtraction, when you plug in your top number, it's that whole thing multiplied by whatever the derivative is there. Okay, that was the only thing that I messed up this morning. Sorry, Math 100 people, but there's your fix. Math 100 people, you already saw these numbers, but here they are again. Calculus 12, who's listening as we speak. Say hi to him, everybody. There you go. 81 to 91, page 290, odd, please. Thank you very much, and have a nice day.